Hello friends, this is Prashant Agrawal, Associate Professor, Department of Computer Applications, Kite Group of Institutions. We are going to start unit number 2 from this video, and in this video we will discuss one of the most important data structure, that is arbitrary. Total 3 videos I will cover to complete this topic. In the first video I will discuss the properties of the arbitrary. In the second video I will cover the insertion, how to insert the element into the arbitrary. In the third video we will discuss the deletion into the arbitrary. So let us start with the first video, the properties of arbitrary. Before starting the arbitrary, we should understand the concept of balancing and unbalancing. Actually what happened, when the first question should comes in our mind, what is the need of the arbitrary? Arbitrary is important as we have already a basic idea about the binary search tree in which we insert a node at the time when the element occurred. But what happened if we go through the binary search tree? Sometimes it becomes skewed, either it becomes the left skewed or it becomes the right skewed. When the tree becomes skewed, it becomes unbalanced. So the question is that what is the balance and what is unbalanced? If the tree is complete binary tree, then it is very easy to say the tree is balanced. The meaning is that the height of the left subtree and the height of the right subtree, if you will try to get the difference between those height, and if it is exactly 0, so easily we can say that my tree is balanced tree. But this property should be followed on each and every node in the entire tree, not only on the root. But if you will construct a binary search tree, it is not always possible as the elements are coming. So always the tree that you are getting, it is the balanced tree. What will happen if the tree is not balanced? The main advantage of the binary search tree is that the complexity of all major operations are always remain order of log n. So either if you are inserting an element, so it complete it into the order of log n time. If you are deleting an element, again it will complete into the order of log n time. The same way the searching will complete into the order of log n time. But all these operations will complete in order of log n time when only your tree is balanced. If tree become unbalanced, that means it is skewed either into the left hand side or into the right hand side. What will happen? The behavior of the tree we will lost and it will behave like a linked list. And in that case, the complexity of all major operation can be grows up to the order of n. So what we need to do? We need to balance such tree from unbalanced to balance. So how this is possible? So there are many ways, many algorithms, many different kinds of trees are available by which that you can achieve unbalanced tree into a balanced tree. So one of that tree is AVL tree, and the second one is the arbitrary. AVL tree, I hope that you people have gone through because in this subject while we are discussing, so AVL we have also discussed in some of the previous subjects. But there is a big difference between the AVL and the arbitrary. In AVL, the rule of the balancing is very strict, so we need lots of rotation to get a balanced tree from an unbalanced tree. In arbitrary, the strictness is slightly different as compared to the AVL tree. So by doing the less number of comparison, we can achieve our tree as a balanced tree. So let us start the properties of the arbitrary. So arbitrary has the 5 properties, and it is my suggestion to all of you, always try to memorize all these 5 properties in which order that in which I am presenting to you, in order in which I am presenting to you. So that means the property number 1 should remain the property number 1. There is no need to resequence all these properties. The first important thing, arbitrary is a binary search tree, that always you should remember. And then let us start with the first property. The first property is that either the node is red or black. It means each of the node of your binary search tree, either it should be red or it should be black. This is the property number 1. And what the property number 2, the root is always black. So there is no confusion about the color of the root. The color of the root will remain always black. And the property number 3, if you will look at the property number 3, all leaves are black. Either we are saying leaves or we can also say the leaf nil. What the leaf nil? Basically In the RB tree, we consider the leaf node as those nodes in which we are not storing our data. We are only storing the nil values in those data. Meaning, what the data in the nodes in which we are storing our data will never be considered as the leaf node. The leaf node will be one of the extra node that having no value, that is having nil value, and what we are saying that the all leaf nils will always be black. And this is the property number 4. The property number 4 is very important. It should be just read it very carefully. All red node must have black children only. That means if a node is red, then both of its children should be black. But there is no property about the black parent. So if a parent is black, its child can be red or black. But if the parent is red, its child should be black only, both of the child. But the property number 5 is, if you are moving from root to descendant leaf by any of the path, the number of black nodes are same in all the path. So what it shows to you, if the tree is there and you are moving from root to any of the leaf by using any of the paths, so the number of black nodes will occur in those paths will always be same. So let us have the look of the figure. This is what the RB tree. And you can say the root is black. You can say all the nodes are either red and black. That very easily you can identify that. The leaf nil, I have not mentioned the leaf nil in this figure. In the another figure I will show you the leaf nil, but in this figure all leaf nil are not present. So that means property number 1, the root is black. The property number 2, either the node is red or black. It is applicable in this figure. And the property number 4, if you look at the property number 4, just look all the red nodes. Just look all the red nodes. And if you look at the red nodes very carefully, you find both of its children are always black. But there are some black nodes are available, and you can see about that black node there is no such rule. It can have red children, both of the children can be red. It can have other way, that means both of children can be red or black, or one of the children can be red or the other one can be black. And now come at the property number 5. So just try to traverse from root to leaf and find out how many number of black nodes you are getting. So if you will traverse from root to leaf, but remember in this figure the leaf nils are not present. But anyhow, let's suppose for the understanding you can see if you are moving from root 20 to the leaf in this particular left hand side, so you can find there are certain number of black nodes. Then these certain number of black nodes will also be same if you are moving from root to the leaf to the right hand side. But there is the importance of the leaf nil, so we are coming on that part also. So now look at this picture. In this picture, because we are focusing on the leaf nil only, so I'm not bothering about the color of the tree. That's why I make it at a single color. But all those nodes will either be red or black. So just look at here. All the nodes having 2 leaf nil. All the nodes. And these nodes are black as per the property 3. And all these nodes will have no value. That means they all are having nil value only. So either you are maintaining the separate leaf nil for all the last node of your tree. You can also make the single leaf nil for all the last node of your tree. That means either to the left child or to the right child you can keep the address of that node only. So by just taking the single node you can fulfill the property number 3. Now let us discuss the property number 5 in a detail. So before discussing the property number 5, let us understand the concept of the black height. If the concept of black height is clear to you, then it is very easy to understand what is the property 5 says to you. What is the black height basically? So in this figure, it is very much clear what is the black height. How will you calculate the black height? That is very important, because black height can be calculated on any node. It is not always that you are calculating the black height from root node only. You can calculate the black height of a node of the tree, any node of the tree. So how will you calculate? So just look at in this figure. So start from the root and try to traverse to the leaf nil and find out how many black nodes are coming in that path. Important thing is that the node on which you are calculating the black height, ignore the color of that node. That means if it is black, you will not count the black of that node. If it is red, then there is no need to count the black of that node because it is the red node only. So in this figure, the root is black. So if we will calculate the black height of the root, so we will not consider the color of the root here. So the second node, what is the second node? Second node is red in the left hand side. The third node is black. So this is the first node that from root to leaf nil we are finding this is the first black node. And then we are reaching to the leaf nil, and this leaf nil is also a black. So how many black nodes we are getting from root to leaf nil? 2 only, because we are ignoring the color of the root. So what is the black height of the root node? It is 2. But this should remain same for all the path. So let us consider some other path for root to leaf, and let us see is the black height is still remain 2 or it may change. Now let us coming from this side. So for the right hand side, let us coming from the right hand side. The black node is there, the right node is red, and then again the black node, and then leaf nil black. So how many black nodes are coming? 2 black nodes are coming. Easily you can compute the black height of all the nodes. So what the property number 5 says to you, this is the property number 5. If you are moving from root to descendant leaf from any simple path, the number of black nodes will remain same. And these number of black nodes will be considered as the black height of that node. Now we will discuss one of the most important lemma of the arbitrary. Because this lemma proves the complexity of all major operation in arbitrary will remain order of log n, as similar into the balanced binary search tree. So the lemma is a red-black tree of n internal node has height at most 2 log n plus 1. So what does it mean, the internal node? Because we are inserting leaf nil externally in our tree, so these leaf nil we are not considering as an internal node. So all leaf nil will be considered as external nodes. So all those nodes which are having data in that will be considered as internal node. So we are finalizing that the number of internal nodes are n, and we are considering the height, the total height of this arbitrary is h. So what is the lemma? If the number of internal nodes are n and the height h, then height should always be at most the height should always be at most 2 log n plus 1. That means it cannot never be less than to that particular value. So how you will prove that? This is the major question. So to prove this statement, first we need to prove these two statements. What is the first statement? A subtree rooted at any node x has at least 2 to the power bhx minus 1 internal nodes. What is the bhx is here? bhx is the black height of node x. And what is the second statement that we need to prove? The black height of any node should always be greater than equal to half of the height of that node. Meaning is that means black height will always be greater than equal to half of the height of that node. What is the height? Height of that node is, that means the maximum number of the height. What is the height of that node? The length of maximum path from that node to the descendant leaf. What is the black height? The number of black nodes we are finding from root to the descendant leaf. So what we are saying in this particular statement, the number of black nodes will always be greater than equal to the half of the height of the tree. So the number of black nodes we are assuming, the number of black node we are considering as a black height of that node. So first we will prove the first statement and later we will prove the second statement. So first statement we will prove by using the concept of the mathematical induction. Just look at the picture and look at the black height of few of the node. Let us consider the black height of all these nodes. If leaf nil are not present in the picture, it does not mean the leaf nil is not present in the system. Leaf nils are here and all leaf nil are of black color. So what is the black height of all these nodes? The black height of all these nodes, if you will reach to the leaf node anyhow, so it will be 1. The important thing is that what is the black height of a child node? If the black height of the X node, let us consider it is B, then what will be the black height of the child node, immediate child node? So it will depend upon the color of that child node. Just look at the root. What is the black height of this root node? 1 black node, 2 black node and one more leaf nil will be the black node. So total number of 3 black nodes are here. So that means the black height of the root is 3. And this root node having 2 children. One is in the left hand side and one is into the right hand side. And this left child having the red color and this right child having the black color. Now what is the black height of this red child? If you will calculate the black height of this red child, again you will find it is 3. But if you will calculate the black height of this right node, that is black, so you will get that it is 2. So meaning is that the black height of the left child is same as the black height of the root and the black height of the right child is 1 less as compared to the black height of the root node. On which it is depending? It is depending on the color of the child node. So now let us apply the mathematical induction. First we are applying the mathematical induction on the leaf nil because the leaf nil are at the height 0. So what the statement we need to prove? The number of internal node at any node x will be at least 2 to the power bhx minus 1. And our leaf nil, let us start from the leaf nil. Our leaf nil at height 0. So there is no path from leaf nil to the leaf nil. So that its black height will also be 0. So how many number of internal node at node leaf nil? So it will be 2 to the power 0 minus 1, it is 0. So that means the first step of the induction is proved. Now we need to prove at first level, then we will consider that into the nth level. So now let us consider a node X with 2 children, one is L and one is R. L is the left children and R is the right children. I have already told you how to compute the black height of the children of the node. If the color of the child node is red, then the black height will remain same. If the color of the child node is black, then the black height will be 1 lesser than to the parent node. So how many internal node a root node can have? A root node can have the number of internal nodes are present into the left subtree plus the number of internal node present into the right subtree plus that node. So a root node can have the number of internal node always be greater than equal to the number of internal node present into the left subtree plus number of internal node into the right subtree plus 1. And how to compute the number of internal node into the left subtree? As per the induction, so we are assuming that it is equal to 2 to the power bhx minus 1 minus 1, because we are considering the black height of the left subtree, it may be reduced by 1. We are also considering the black height of the right subtree, it may also be reduced by 1. So what we are doing, we are taking the number of internal nodes from the left subtree plus number of internal nodes from the right subtree, we are adding them together and then we are adding the root node in itself. Then we are saying the total number of internal node in the system will always be greater than 2 that equation. So the equation is 2 to the power bhx minus 1 minus 1 plus 2 to the power bhx minus 1 minus 1 plus 1. This is the number of internal node into the left subtree. This is the number of internal node into the right subtree, and this is the root itself. If you will compute it, so you can simplify this, and you will find that the number of internal node at root x is equal to 2 to the power bhx minus 1. This is what we were proving. So it means our first statement is proved as per the mathematical induction. Now we are coming to the second statement. What the second statement is that? The black height of any node will always be greater than equal to the half of the height of that node. How we can prove that? By the property number 4, easily we can prove it without applying any of the mathematical approach. What it means? Because the property number 4 told to you that each of the red node must have black children. What does it mean? It means the two red nodes can never be together, but two black nodes can remain together. That means black parent can have the black child, but the red parent cannot have the black child. But the red parent cannot have the red child. Red parent must have the black child. So what can be the maximum length in a tree that you can find of the red black? So the node can be red, the other can be black, the second node, the another. So what is the maximum length that you can find of red black? If the one node is red, then its children can be black, then its children can be red, then its children can be black, then its children can be red, then leaf nil can be black. And what is the shortest path that you can find of a node? So the one node is black, then its child is black, then its another child is also black. So what the relationship? The relationship is very much clear that half of the node is always, it must be black in any of the path. So meaning is that the black height of any of the path must be greater than equal to the half of the height of that tree. So it means the property number 4 is sufficient to fulfill that second statement that what we need to prove. So as both of the statement is proved, now what we can say is for the root itself, we can say the black height of the root is greater than equal to the h by 2, and the h is the height of the tree. And for n number of internal nodes, what we can write? So what we can say as per the statement 1, the n is greater than equal to 2 to the power black height of root minus 1. And the black height of root can be replaced by the h by 2 because the sign is same in both of the statement. So what we can say, the n is greater than equal to 2 to the power h by 2 minus 1. So by simplifying them, that take 1 into the left hand side, then taking log of both of the side, easily we can prove that h is less than equal to 2 log n plus 1. And this is what we were trying to prove. And this statement helps us to compute the complexity of all the operations of arbitrary, because it proves the complexity of all major operation will be order of h into the arbitrary. So if we ignore all the constant terms plus 1 upon 2, so easily we can say the complexity of all major operation into the arbitrary will be order of log n. So thank you friends. In this video we have covered the properties of arbitrary, the look and feel. We have understood of how the arbitrary is look alike. We have discussed one of the good lemma of arbitrary, that establish a relationship between number of internal nodes and in the height of the tree. In the next video we will discuss how to insert a node into the arbitrary without violating its properties. So thank you friends.